So the additive inverse of a vector in the space is going to be negative v1, negative v2, negative v3. Why is that? Because you have object, your vectors of the form of v1, v2, v3. So the additive inverse is basically multiplying every component by negative value, negative 1. So you get negative v1, negative v2, negative v3. Remember that if you add v and negative v together, it is equal to the 0 vector. Now, if you are in the vector space of all continuous functions between negative infinity to infinity, in this world, the additive inverse of a function is negative that function. You're basically looking at the reflection with respect to x-axis. And again, if you add these two functions together, we get 0 function back. Now consider the vector space of all matrices are all 2 by 3 matrices. If you take an element like a vector in this vector space, these are all matrices, A sub 1 and 1, A sub 1 and 2, A sub 1 and 3, A sub 2 and 1, A sub 2 and 2, A sub 2 and 3. So you have 2 rows and 3 columns. The additive inverse is calculated by multiplying negative 1 or negative sign by every single entry, which is basically the scalar multiplication. So the additive inverse of this matrix is going to be this 2 by 3 matrix. And again, if you add these two vectors together, we get 0 matrix back. So in each vector space, we have different types of vector, everybody. Now, the question says, determine the set together with the standard operations is a vector space or not. If it's not, identify at least one of the 10 vector space axioms that fails. Here we go. Consider this set, the set of all ordered pairs x and y such that x is more than or equal to 0 and y is any real number. Perfect. So if I graph this, this is the shaded region on the right-hand side of x equal to 0. X equal to 0 is also included. X equal to 0 is just y value. So this is this set here. Now, this set is not a vector space. Why is that? Because the set is not closed under scalar multiplication. How so? For example, if I take negative 1 and multiply this vector, which is 3 and 2, by negative 1, I get negative 3 and negative 2 back, which is not in this set. So take a look. I have 3 and 2, which is just this point here. If I multiply it by negative 1, I get negative 3 and negative 2, which is basically a point here, negative 3 and negative 2. But as you can see, this point is outside the shaded region. This point is not in this space. So basically, C times U is not in V. It's not closed under scalar multiplication. So this is not a vector space. Okay, perfect. Next example for you. The set of all 2 by 2 singular matrices. Is this guy a vector space? Well, let us take a look. We need to check these axioms, 10 axioms that we have. This set is not closed under addition. Why is that? Can you come up with an example? Sure, we have 100 examples here. Consider these matrices. The very first matrix is a singular matrix. Why? The determinant is equal to 0. The second matrix is a singular matrix. The determinant is equal to 0. But if I add them together, I end up with identity matrix, which is non-singular. So you're adding two singular matrices, but this new vector is not singular vector, is not a singular matrix. So it's not in this set. It is not closed under addition. So again, the determinant of the first matrix is 0. The determinant of the second matrix is 0, but the determinant of the third matrix is 1. So basically, this is not a vector space. Okay. Next example for you. Prove in full detail that the set of all 2 by 2 matrices with standard operations is a vector space. So what are we going to do? We're going to start by checking these axioms. Okay. First of all, we need to check to see if the addition of these two matrices is a 2 by 2 matrix or not. So you're going to take a random 2 by 2 matrix, not numerical values. It's a common mistake for students that take random values. You cannot take random values. When you're proving properties, you have to work with general elements. U sub 1, U sub 2, U sub 3, U sub 4, V sub 1, V sub 2, V sub 3, V sub 4. Add these together. So you're basically taking the very first entries, add them together, the second entries, add them together, and so on. This is basically a 2 by 2 matrix. You can easily see that. And then if I add U and V, it must be equal to V plus U. There shouldn't be any difference between them. So if I add U and V, I have U1 plus V1, which is U1 plus V1, the first entry of this new matrix. But I can switch these two. This is just addition of two. Let me erase that. It's just addition between two entries, two elements. All right. So now you're adding two numbers together. Basic algebra. U1 plus V1 can be written as V1 plus U1. U2 plus V2 can be written as U2 plus V2 plus U2, and so on. So you're basically saying that, hey, I'm taking the second matrix and add it to the first matrix, so I can easily switch the order. So far, the first condition is met. The second condition is also met here. Now, we can go to the next slide. The third property says, hey, U plus V plus W must be equals to U plus V plus W. So I'm going to take three matrices. I'm going to write down the general entries, not just some numerical entries, everyone. Because it's a common mistake for students that they're taking just some matrices and add them together. Hey, you have to use general definition. U1, U2, U3, U4, V1, V2, V3, V4, and W1, W2, W3, W4. Add these together, but these two comes first. So you're going to add these elements first. Then you're going to add U1 to V1 plus W1 and so on. But this is basic algebra. I can easily group these together. I can group U1 and V1 instead of grouping V1 and W1 and then add it to W1. So now you're basically saying that, hey, I'm adding U1, V1, U2, V2, U3, V3, U4, V4, and then W1, W2, W3, W4. Or basically, I'm grouping U and V, add them together, and then add it to W, which is basically U plus V plus W. So this is the third condition. The third axiom is met. So we proved the first axiom, we proved the second axiom, we proved the third axiom. Let us move on to the next slide, everyone. For the fourth axiom, we're looking for zero vector. The zero vector in this case is a 2 by 2 zero matrix. U plus 0 is a 2 by 2 matrix. U1, U2, U3, U4 plus this zero matrix 0, 0, 0, 0, which is basically nothing but adding the entries, corresponding entries together. U1 plus 0 is U1, U2 plus 0 is U2, U3 plus 0 is U3, U4 plus 0 is U4, which is basically U. So the fourth condition, the fourth axiom is met as well. What about the fifth axiom? If I add U and the scalar multiplication of U by -1, if I add these two together, do I get zero matrix back? It should be easy for you to verify this. U1 minus U1 is 0. U2 minus U2 is 0, and so on. So if I add these two vectors together, it is equal to the zero vector. So far for addition, the first 5 axioms is met. Now we're going to move on to scalar multiplication. For the scalar multiplication, you have C times U. So C times U is the scalar multiplication of C by matrix, this 2 by 2 matrix, which is basically taking C and multiplying every single entry by C. Is this a 2 by 2 matrix? Of course it's a 2 by 2 matrix. This belongs to this set. So 6 is also met. Now, can I distribute C over the addition? If I take two matrices, add them together, and then find a scalar multiplication, this is basically multiplying every single entry by C. You're basically doing algebra now. You're multiplying C by U1 plus V1. You're multiplying C by U2 plus V2. You're multiplying C by U3 plus V3. You're multiplying C by U4 plus V4, or from algebra, it's just simple distribution. So now you can separate these two matrices, and then by the property of scalar multiplication, you can write C in front of the first matrix and write C in front of the second matrix. Or basically you have CU plus CV. This is the seventh axiom. 8, 9, and 10, everybody. It should be easy for you because these are basic algebra. C plus DU is basically C plus D, and U is a 2 by 2 matrix. Now what are we going to do? We're going to basically do the scalar multiplication. C plus DU1, C plus DU2, C plus DU3, C plus DU4. From this step, you're doing simple algebra. CU1 plus DU1, CU2 plus DU2, CU3 plus DU3, CU4 plus DU4. Now you can basically separate these two matrices. The addition of CU1, CU2, CU3, CU4 plus DU1, DU2, DU3, DU4. Basically, you're using a scalar multiplication. C times the first vector plus D times the same vector. So basically you have CU plus DU, which is the axiom number 8. For the axiom number 9, C times DU, this is basic scalar multiplication. You're just finding the scalar multiplication of C and DU, DU1, DU2, DU3, and DU4. Now, based on the definition of scalar multiplication, This becomes CDU1, CDU2, CDU3, CDU4. Now, what we learned from algebra, we can group C and D together now. So that's how you end up with CD grouped together in parentheses multiplied by U1. Now, using the scalar multiplication property, you can write that CD multiplied by vector U. This vector is nothing but a 2 by 2 matrix. Finally, number 10 for you. 1 times U is the scalar multiplication of 1 by this vector, which is 2 by 2 matrix. U1, U2, U3, U4. From a scalar multiplication, it is 1 times U1, 1 times U2, 1 times U3, 1 times U4, which is basically U itself. So all of these axioms are met. What's the meaning of that? It means that you have a vector space. So on the exam, if I ask you to prove a set is a vector space, you need to patiently prove each one of these axioms.